Hi there, folks. Thanks for joining me once again. It's Root Beer here, and we're going to be starting another contest, the 2005 Galois contest. So, before you watch any further, as always, I try to encourage you guys, click the first link in the description, download a copy of the contest for yourself, and try it out. You get 75 minutes, so print out a copy, try it for 75 minutes, see how far you get, see which questions you can answer, which ones you don't, then come back and watch. It's the best way to learn, is to try things out for yourself. But I'm going to assume you've paused the video and done that. Grab your pen or pencil, actually pencil's probably preferred, and let's take a look here at the Galois. So it's only the third year of the contest. They don't have the fun stuff, the preamble that says, you got this much time, calculators allowed, that sort of thing. That'll come in later years. So like, for example, the 2005 Gausses had that, but not the Galois yet. They were still experimenting with this one. Alright, so let's get started with question number 1. An arithmetic sequence is a sequence in which each term after the first is obtained from the previous term by adding a constant. Okay? So if you didn't know what an arithmetic sequence is, which you hopefully should, either for this contest or for future contests, a very nice concept, arithmetic sequences and geometric sequences. These are quite nice to be able to work with. But if you didn't know that, there's a nice handy definition. So, for example, the sequence 2, 11, 20, 29 is an arithmetic sequence. It starts with 2, and then to get to each subsequent term, we add 9. So 2 plus 9 is 11, plus 9 is 20, plus 9 is 29. The dot, 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 or ellipsis, I believe that's called, indicates that this sequence continues forever without ending. All right. So we got 3 parts to this question. A, find the 11th term in the arithmetic sequence 17, 22, 27, 32. And we have to remember the Galois, like the Friar and Hypatia contests, are written contests. So we need to explain a little bit what we're doing in order to get full marks. So we'll open up our notepad, and the sequence that we're starting off with here, 17, 22, 27, 32. Okay, so this is the first term, second term, third term, fourth term, and we want the 11th term. Now, you could just 11 is a very small number, relatively speaking, so you could just keep going with this sequence until you get to the 11th term. And if you don't know what an arithmetic sequence, or if you didn't know what an arithmetic sequence is, then that's likely the best way to go about doing it. And you would earn full marks because you have shown exactly why it's 11, because you wrote everything out. You might want to make a comment about how we're getting each new term, like what number we're adding, and that's something I'm going to do. So I might say something like, we can see that we add, because the difference between any two of the terms has to be the same thing. We can see that we add 22 minus 17 equals 5 to each term. So if you wanted to, you can then say, well, the 5th term is 37, the 6th term is 42, that sort of thing, and you can keep going. But there's another way to do this question. In general, arithmetic sequences start with a first term A, and have, so this number 5 here, he's typically called the common difference. And the nice thing about this is the nth term of the sequence is A plus n minus 1 d. You do the n minus 1 because the first term should have no extra d's added onto it. It should just be the a. Okay? So this is a bit of sort of arithmetic sequence theory out there for you. You don't have to be this general. I'm sort of bouncing between two extremes. The write everything out and the give a general arithmetic sequence definition and generalization. There's probably some middle ground where you can say, oh, the common difference is 5. I need to add 10 of those on to get to the 11th term. So 17 plus 50 is, and then you get 67, which is going to be our answer. Okay, so there's sort of three styles of way we could do this one. Just write everything out without thinking, write the super general stuff that I'm doing here, or a happy medium where you recognize the common difference and you add on 10 copies of it to get to 11. If you wanted 12, you would add on 11 copies, so you'd add on 55 to 17. So one might say A is 17, D is 5, and the 11th term is 17 plus 11 minus 1 times 5, 17 plus 50, 67. Okay, that's a fantastic way to do it. But no matter how you did it, one of those three ways, or even a hybrid of any of them, we get the answer to A. It's a nice little introductory question. Do we really understand what arithmetic sequences are? Okay. So, B part. Explain why there is no number which occurs in each of the following arithmetic sequences. 17, 22, so the one we started with. Okay. 13, 28, 43, 58. Okay. So the first sequence is starts with 17, goes up by 5s. This sequence, what's going on? 13 to 28, that's a difference of 15. So we're not going up by 5s, we're going up by 15s each time. Okay. So, how might we approach this question? So we've got 15 or 17, 22, 27, 32, and so on. And then we have 13, 28, 43, the next one is 58. Okay. So what are we to do? Okay, why can't these eventually intersect, that sort of thing? So I might, using my really general language, write something out like this, and then maybe we start another one with B is 13 and a common difference of 15. That would be perfectly fine. And then we could say, well, if there were, if nth term in one sequence equals the nth term in the other, we have formulas for those. So A plus n minus 1d has got to be B plus m minus 1e. Okay? This is a nice, very general way to do it, but you don't have to. And since I did A part very generally, I'm actually not going to proceed this way for the question. I like to bounce around because I have a feeling that if you're watching this video and I just start jumping in with all this stuff, and if I keep doing everything like that, it'd be perfectly fine if you already understood that, but this isn't going to be a great learning technique if you're like, why are you doing A plus n minus 1, and how did you know to set those up, and why are you using an n and an m, why can't you use the same n? Those are all great questions, so we're going to avoid them. We're going to vary our technique a little bit here. Okay? So let's get back to the question. There's a much simpler observation we can make with this question. So our sequence is 17, 22, 27, 32, 37. The other one is 13, 28, 43, 58. What would be the next one? 68 plus 5, 73. Okay. The simpler observation is our difference up here is 5. We've already noted that. And the difference here is not that hard to see. It's 28 minus 13, which is 15. The thing here is 15 and 5, these are both multiples of, they have a non-unit greatest common divisor. So the thing that we need to note is these guys are going to have sort of the same remainder when we divide by 5. So notice that each term in the first sequence leaves a remainder of 2 when we divide by 5. This is a nice, quick observation to make. If you wanted to justify it a bit more, it's because we add 5 to each term, so the remainder isn't going to change. But I think this is perfectly fine to say. And now we don't want to use 15, we want to use the 5, because 15 is a multiple of 5. So we're not going to change there, and then so you can say, notice that each term in the second sequence leaves a different remainder, a remainder of 3 when we divide by 5. So let's suppose that number x was in both sequences. Then x leaves a remainder of 2 and 3 when we divide by 5. This is, you could say silly or a contradiction or absurd is probably a better way of saying silly. So no such x exists. So this would be a faster way just based on remainders. Okay? You don't have to set up any ridiculous, very general terms. You could, but your argument at the end of the day for what we sort of decided not to do will still be based on the fact that we've got 2 common differences. One is a multiple of another. And that when we take a look at remainders, we get a different constant remainder for the terms. Okay? So that one's not so bad, and that writing that I've done there is exactly what I would write for the 2005 Galois, for really any Galois if I were writing it. I have stated some things. For example, the difference is 5, the other difference is 15. Those are quite clear. I have made note of the remainders. I don't think it's necessary, certainly not for the 10th grade level contest, to have to prove that it's always going to be a remainder, especially because it's question 1. Maybe for a Hypatia, or maybe for someone who's really, really worried about losing marks. But no, we just notice the first term, constant remainder 2, next term, constant remainder 3. This will lead to an absurdity if you have a number in both sequences, the same number in both sequences. So that would be maybe 4 marks, maybe 1 for the difference of 15, because we already know the difference of 5 from the previous from A. And then observation of remainder 2, observation of remainder 3, and then contradiction that you can't have both. But that's optimistic. I mean, this one was probably worth maybe 3. Anyway, that's B part. Let's take a look at C part. C. Find a number between 400 and 420 which occurs in both of the following arithmetic sequences. So we've got 17, 22, 27, 32, the same one that's been following us the whole time. 16, 22, 28, 34. So we've got 22s in common. That's nifty. But 16, 22, 28, so a difference of 6 here. Okay. Now, because 6 is not a multiple of 5, 5 is not a multiple of 6, we should expect some intersections, some overlaps. Indeed, we've already got one staring at us in the face there, 22. So we might, if we didn't, depending on whether or not you know arithmetic sequences, you might start jumping into this thing and realizing, well, 6 times 5, 30, 52 should be in both sequences. You might be able to make those sorts of observations, but let's suppose we didn't. Let's investigate these sequences. So I noticed 22 We get 22 in both of them. 40. So you might make the observation difference of 6. Okay. We get 46, and we get 52 here. We can keep extending. So we have 58 here, but 37, and then it was 42, 47, 52, 57, and we can keep going, but notice the 22s are in common, the 52s are in common. What are these guys? Why those ones and not any others? And we could keep going, 62, 67, 72, 77, 82, and 82 is as far as I'm going to need to go, but we'll do 87. 58, 64, 70, 76, 82, 88, and so on. And we've got another pair in common. So at this point, you might try and suspect, well, 22, 52, 82, I'm noticing a common difference of 30. And why would common difference be what we look at? Because they're arithmetic sequences. So you might expect, although, if this is your first time looking at arithmetic sequences, you can't be guaranteed of this much, but you might expect that common terms in two sequences would also then form an arithmetic sequence. Okay? But, we need to justify this. We need to explain it to the written contest, not a multiple choice one where we just figure out the pattern, generalize it, extend it, and everything. We got to explain what we're talking about. So we do this amount of work, and then we sort of start seeing, okay, 22, 52, 82, and nothing in between them seems to work. So why is that? Well, I might say notice that 22, 52, 82 are in both sequences. Okay. So, starting from 22, how do we get to 52? So 22 is 22 is the second term in the first sequence. And 52 is the 1, 2, 3, 4, 5, 6. So 2, 3, 4, 5, 6, 7, 8. He is the 8th term in the first sequence. And 82 is the 8, 9, 10, 11, 12, 13, 14, 14th term. Okay. So we might notice a little something going on there. It's a difference of 6. Where have we seen a difference of 6 before? Right over here. So to get from 22 to 52 in our first sequence, 22 plus, well, how many of the common difference of 5 do we need? We need 6 copies of our common difference of 5. Okay. So I might even say add on 6 5s. But we could rearrange this equation to say 22 is 5 6's being added on. It gives us 52. 52 is 22 plus 5 6's. So since 5 is a common difference in our first sequence, and 6 is a common difference in our second sequence, we can see that if, I'll go to the next page for this statement. If x is in both sequences, then x plus 30 is in both sequences. And if you wanted to, you could say, well, x plus 30 is x plus 5 times 6, just as we already noted, but it's also the same as x plus 6 times 5. Okay, so if x was in both sequences, then 5 terms down the road, we're going to see x plus 30 in the second sequence, and 6 terms down the road, we're going to see x plus 30 in the first sequence. Okay, you could justify it. You could write out a bit more, but I think it's clear from there. So we understand the pattern. So we're looking for a number between 400 and 420, which looks like 22 plus some number of 30s. Okay, well now this isn't particularly hard to find. Okay. So we can say something like 400 is less than or equal to 22 plus 30y, less than or equal to 400. There's lots of ways you could go about doing this one. I'm going to subtract 22 from both of them, so 378 less than 30y is less than 398. And if I divide by 30, this guy is going to be a little bigger than 13. And this guy here is going to be a little bigger than 12 for y. Y equals 13 will do. There's lots of ways to show that. So 22 plus 30 times y, 22 plus 30 times 13, 22 plus 390, and then 412. 412 is in both sequences. Okay. We've justified it. We took a look at the patterns. We noticed that common numbers are 30 more than the last common number. We explained why that is. Common difference of 5, you add 6 of those. Common difference of 6, you can just add 5 of those. So you're always going to get x plus 30. And then we said, okay, now what did they want? They wanted a range of 400, 420. Very quickly, we get y is 13, and we get 412. Okay? So that was C part, and that is the last thing we need to do in question number 1. Interesting little experiment with arithmetic sequences. In the next video, we're going to take a look at question number 2, which appears to have a game. And it's got 3 parts. I can't wait to take a look at that. And if you haven't already, try that one out for yourself, and then watch the video. I'll see you guys there.